Okay, thank you. So my intention is to give a short talk, knowing that it's a long day, and some of you still have dinner to look forward to with the rest of the group. Okay, um, so let's see. So I guess to begin, my idea was to sort of preach a sermon about you know algebraic cycles and sort of it's a great subject, I think, but it has the difficulty that it seems like everything you have to do by hand. And so those people who invent a machine that allows you to do a lot of things deserve a lot of credit. So, something like in topology, in the old days, say in the 30s, you had to do everything by hand, but then in the 50s, things like spectral sequences were invented that allow you to, that were sort of tools that people could use for many, many years afterwards. So all credit to those who invent good machines in the theory of algebraic cycles. Um, um, and yeah, so some of the ones that sort of, I mean, of course, there are innumerable things that can be described that way, but I mean, some of the ones that came up this week that I'm very fond of are derived, the derived category of motives, or more generally, A1 homotopy theory. So, as, developed by people like Borel and Vygotsky and others. So people have always imitated homotopy theory in algebraic geometry, but there's really something to be said for making a precise category where essentially everything in homotopy theory can be imitated. Another one, in a sense of a very different direction, is this argument about decompositions of the diagonal. So I won't really try to describe this, but basically this is a kind of very short argument about the relation between how Chow groups of a variety behave when you enlarge the base field and the Chow groups of just something like the product of the variety with itself. It's somehow a very short argument, but it has been possible to play with this for more than 30 years in the theory of algebraic cycles. So people like Srinivas developed one famous version of this argument in the 80s, but since then many of the speakers at this conference developed it a lot further, for example, to say something about birational geometry. So, let's see. And then another one, well, of course, it's completely vague what you want to call a machine, but another one which I'm enthusiastic about from the sidelines is sort of just I want to say sort of just using number theory systematically. So I'm thinking about things like so by Sophie Morel and Jun-Kyu Su to prove things like the sign conjecture, which is part of Grothendieck standard conjecture, not for all varieties or anything, but for many Shimura varieties. And the philosophy of Langland's theory is that in some sense, Shimura varieties are the most important of all varieties. They should be sort of related to the cohomology of all varieties. Or another thing would be Bergeron and his collaborators on proving the Hodge conjecture for in some range of degrees for many Shimura varieties. So yeah, okay. So it just sort of seems like there are a lot of tools there in number theory, which sort of, by general arguments about algebraic cycles, we seem to be very far away from that kind of thing. Okay, so in this talk, I wanted to talk about a particular machine that I like lately, or describe it as a machine, which is the idea of studying Chow groups mod P of a complex variety by relating them to the reduction of that variety mod P to somehow, if you imagine X as defined over some number field or something, you could consider the corresponding to let's say, properties of the reduction of x to characteristic p. So there's a sort of a vague way of putting it, but it seems like there's enough that you could do that way that this is, well, you always still need to do some work by hand, it seems, but it's getting much more like a general machine. Okay, so, right. So yeah, in particular, I gave this example of complex varieties with infinite Chow groups modulo 2 using somehow this idea, yeah, there's a long history to this idea, some of which I'll describe first. So, right, so yeah, kind of one origin of this sequence of ideas is the result by Griffiths and Clemens that for a very general quintic threefold over the complex numbers, so you can look at the Griffiths group that is a group of codimension 2 cycles, that is one-dimensional cycles that are homologically equivalent to 0, modulo the ones that are algebraically equivalent to 0, the cycles that you can connect to 0 by a continuous family of cycles. This is sort of obviously, I mean, this group could well be uncountable, but this quotient is more or less obviously countable because you're sort of dividing out by all the continuous families of cycles. It's a countable abelian group, but it's otherwise sort of as big as it can be. So this group tensor Q has infinite dimension as a Q vector space. Okay. So, right. It was quite discouraging, I suppose, in the sense that Grothendieck expected that this group would just be 0, but it's not. Okay. Okay. Then the particular line of thought that I'm talking about is comes from another paper by Nori, where he shows, I mean, the same thing happens, but for different class of varieties, namely general abelian varieties of dimension 3, and somehow the good thing about that is that I would say the argument becomes easier in this case. So let's say same conclusion for x. Very general, of course, means when you have a moduli space of varieties, property holds for very general varieties if it holds for all those outside countably many lower dimensional subsets. For very general, say, principally polarized abelian variety of dimension 3, again over C. Again, the Griffiths group tensor Q is infinite dimensional. So to do this, to prove this, in any case, you've got to write down infinitely many interesting elements of this group. And Nori did that using what are called Terasa cycles. So quickly describe. So, right, so it's a special feature of abelian varieties in dimensions up to 3 that they're, most of them are just Jacobians of curves. So here, so since the dimension is at most 3, x is, well, most abelian varieties, in particular a very general one, is isomorphic to the Jacobian of some curve, smooth projective curve of genus 3, since dimension is equal to 3. So, right, so that sort of gives you a certain obvious algebraic cycle on there. So let's just, there's an issue about base points, which I will try to ignore, but if you pick a point in C, then this gives an embedding of the curve into its Jacobian, and what's called the Terasa cycle is C minus, it's written C minus, in group of 1 cycles on the Jacobian. So this means you apply the automorphism of the Jacobian given by -1 to this curve. Say you make the curve go through the origin. Here's 0 on the abelian variety, here's the curve, and here's its negative using the group structure. Okay. So the point is that, so -1 as an automorphism of the Jacobian acts by, say, -1 to the j on H2J of the Jacobian, just because it's pretty obvious, and so it acts. This automorphism acts by the identity on cohomology in even degrees. This is maps to H sub 2, so so C minus its negative this way is homologically 0. Okay. Yeah, thank you. Okay. So in even degrees it acts trivially, and so this is 0 in cohomology, but it's not obviously 0 as an algebraic cycle, and in fact, Terasa showed that it's usually not. So, so for C very general of genus 3, or in fact, you could define this in any genus, but the Terasa cycle is not 0 in Chow groups, the Chow group of one-dimensional cycles mod algebraic equivalence tensor cube. Okay. Okay, so that's how you get sort of one non-zero element of the Griffith group for a general abelian threefold. Okay, how do you get a lot of elements? You just move that around by using isogenies. So I'll explain. Let's see. So for an isogeny that is a homomorphism of abelian varieties that's onto and with finite kernel, suppose these are both principally polarized. Say these are dimension 3. Well, again, in most cases, both of these will be Jacobians. There's a lower dimensional set where that's not true, but let's ignore that. So X will be the Jacobian of one curve, and Y will be the Jacobian of some other curve. And so you have sort of two different Terasa cycles. There's no very obvious relation between these two curves, but nonetheless, so we have C minus Jacobian of C, and the Terasa cycle on the other Jacobian. And you can, if you just want to work with one abelian variety, you can just pull back the Terasa cycle here to get a cycle here. So F upper star of this is also a cycle in this one abelian variety. So by considering, you can easy to see that there are infinitely many different isogenies like this, and so you get infinitely many different, possibly interesting one-dimensional cycles on a general abelian threefold. Now, and yeah, and Nori shows that for most abelian threefolds, those cycles that you get that way are independent mod algebraic equivalents. Okay. Right. So then let's see. There's the question of whether these cycles are 0 in the Chow group's modulo prime number. Let's see. That was essentially was first answered in many cases by Chad Shun, who showed the following. So consider, I showed several results related to this, but one is if you just take the product of 3 copies of the Fermat elliptic curve, x cubed plus y cubed plus z cubed equals 0, then right. And let's see, the codimension 2 Chow group, or Chow group of one-dimensional cycles on their modulo prime number L is infinite for lots and lots of prime numbers, for all primes L congruent to 1 mod 3, which I believe are the primes where that elliptic curve has ordinary reduction. Oh, thank you, thank you. Right, so this is talking about X, the thing of it over Q bar. Thank you. Yeah, so we expect that varieties over number fields have finitely generated Chow groups, but yeah, over Q bar you have this. So of course this implies that the Chow group itself is not finitely generated. And I should make the point that so by Suslin rigidity, that's the same thing as the mod L Chow groups of the same variety considered over the complex numbers. So this is also infinite. Okay. Yeah, and so this argument, I feel like this is really the opposite of an argument by machine. It's like a 60-page paper, and I feel like even after I understand the general idea, it's still really hard. But yeah, so I want to discuss sort of easier results in the same direction. Oh yeah, in particular, the cycles that Shannon used are not these Terasa cycles, but rather it's more like the idea of Noether-Lefschetz cycles. So you relate X to some self-product of an abelian surface over P1, I guess, and you look at sort of which of the fibers have complex multiplication. That there'll be sort of infinitely many fibers that do have complex multiplication. And those fibers have extra algebraic curves sitting in them, and those are the curves that he uses. Anyway, it just turns out, though, to be a very hard argument, and that was sort of simplified a lot by Rosenschön and Srinivas, although they got a sort of different conclusion, not about a very special elliptic curve like that, but rather sort of more like Norrie, so for a very general, principally polarized abelian variety X of dimension 3 over C, they show that the Chow group of codimension 2 cycles modulo L is infinite for almost all primes L. Okay. So, right, so somehow this is maybe what you would expect. I mean, I think, so we know that this group doesn't have all that much torsion in it by results like Merkoriev-Suslin. So, you know, probably this group has a sort of big free abelian group, and then it should be infinite modulo all primes. But anyway, this is what their argument gives. And as I say, it's a much kind of easier version of Schoen's argument, much closer to Norrie's argument. Okay, but it does use the idea, actually, yeah, both of these things use the idea of studying a Chow group of a complex variety mod of prime number by relating it to how the variety reduces mod L. And I'll say a little bit more about how that works. Okay. Okay, so then, yeah, then finally I showed that the same thing holds just for all prime numbers L, and that's the same holds for all primes L. Yeah. And, you know, this is maybe the interest is just the first example of a complex variety of any sort, such that, for example, the Chow groups mod 2 are infinite. Yeah, okay, so that's not surprising if this happens, but technically, sort of working at the prime 2 looked a lot more frightening with the earlier arguments. It sort of has to do with p-adic Hodge theory when the prime is 2, but it turns out that, you know, that you can say things in a way to avoid any difficulties about p-adic Hodge theory. So let me try to outline this proof a little bit. I would say that the thing is, maybe, you know, the good thing is that somehow by now, after Norrie and all these works, the subject is getting pretty close to being a machine, so that this is not a long argument. Okay. All right, so let's see. So sketch of the proof is going to something like this. Somehow the main point is just to argue that for most principally abelian varieties of dimension 3, the Terasa cycle is not zero. Well, I want to say mod L. I might have to weaken that a little bit. So the main step is to show that so for this very general abelian threefold, the Terasa cycle, don't really have a name for that. It's a codimension 2 cycle on X is non-zero modulo L to the C. So for X is above, and for any prime number L, the Terasa cycle is non-zero modulo some power of that prime number L. So, okay. I mean, in a way, this is just this was the one change that I had to make the previous argument. So in the earlier arguments, people show that the Terasa cycle is non-zero modulo L itself. But if you're willing to be just a little bit more flexible, then it turns out not to be too hard to show that. And let's see. Oops, sorry. So, yeah, so why is that really the main step? So at that point, so then it just follows that sort of all the pullbacks of the Terasa cycle by isogenies are also non-zero modulo that same sort of number. So now this is easy because we're just talking about really you could imagine talking about just the generic principally polarized abelian variety, that is work over the function field of the moduli space of all abelian varieties. Then instead of trying to prove something about a whole bunch of abelian varieties, we're just talking about one kind of universal abelian variety. And if you apply an isogeny to that, it's really the same universal abelian variety looked at from a slightly different point of view. So okay, so you get this kind of statement, and okay, you want these different pullbacks to be also independent, not just all non-zero. And somehow, yeah, to get to that last point is that, well, then you want to show that these pullbacks of the Terasa cycle are independent, to put it a little vaguely, in the Chow groups of this general abelian variety mod a certain power of L. So this step is not hard, actually, because you can sort of look at how the Galois group of this relevant field, the function field of the moduli space of abelian varieties, you can look at how it acts on these different cycles. And basically, it acts in a different way on all these cycles. It acts by a certain character, and it's just a different character for all these cycles. So once you know that they're not zero, then they're also sort of just automatically independent as well. The relevant Galois group just acts differently on all the cycles. So somehow, I mean, there's a little pleasant geometric argument in there, but really the main work is to do with just this first part, that's showing that you can write down one cycle that's non-zero modulo a certain power of whatever prime you want. Okay. Yep. Yeah, that's right. You can sort of, sure. You certainly take isogenies prime to L. Okay, so then, how do you show that one particular cycle is modulo, is non-zero modulo some power of a given prime number? Yeah, I will not try to do this whole thing, but let me state sort of the very key ingredient, sort of the key step is a result by just is a theorem by Bloch and Hinault. Which you could say is, it follows from Bloch and Cato's work on p-adic Hodge theory. So this is a kind of very old result from the early 80s on p-adic Hodge theory. The subject has kind of progressed a lot since then, but they only needed a kind of early bit of the subject. So it's like the following. It's the following thing. So let you take a field with a discrete valuation, and I think I want the field itself to have characteristic 0, and the residue field should be perfect of positive characteristic. Okay. Let's see. And you consider a smooth projective variety over that field with good reduction at this evaluation. And I asked that the reduction also be ordinary. So all the eigenvalues of Frobenius have the same p-adic absolute value on each group hi at V, so to speak. So it's really this evaluation is so it's really a smooth projective scheme over the ring of integers of this field. Okay, right. So assume there are a few assumptions. Assume that the crystalline cohomology, but fairly mild actually, the crystalline cohomology of X is torsion-free, which will certainly be true in the cases that I'm talking about, where X is basically where X is an abelian variety, and that yes, thanks. So maybe Y is called a special fiber. Yeah. Thank you. And it's just for a certain number m, the special fiber has some non-zero differential forms. Okay, so it's yeah. So let me just state the conclusion and then comment on that. So then the Konevo filtration on the cohomology of this variety in characteristic 0 with Z mod L coefficients is non-trivial. That's all it says. So this is okay. Or equivalently, what that says is that there are some cohomology classes on X on this variety characteristic 0 that remain non-zero when you restrict them to the function field of X. So the map from cohomology of X with FL coefficients to the cohomology of the function field, so smaller and smaller open subsets of X, that map is not zero. So, I mean, in a way, this seems like quite a weak conclusion, but it is enough to do a lot with, it turns out. Right, so how should I comment on that? Well, the basic point is that somehow, if we were just talking about everything in characteristic 0, then this would be a very familiar sort of fact. So it's just the fact that if you have a variety in characteristic 0 that has some differential forms, yeah. Well, yeah, okay, that's right. So this is X over K bar, and this is the function field, yeah, over K bar. Thanks. Right. So if sort of everything in characteristic 0, this would be totally unsurprising. If you have non-differential forms, then sort of Hodge theory tells you that cohomology, say with rational coefficients, is not all supported on some divisor, which is another way of saying this. But somehow the issue here is if you want to understand algebraic cycles modulo prime number L, you know, and how that's related to cohomology with Z mod L coefficients, then you can do it, but you have to contemplate this variety in characteristic L, I believe. Sorry, I probably want this number L to be. Yeah. So I hope I'm usually sticking to L for that number. So, right. So you want to understand the Chow groups of complex varieties mod L, you have to think about varieties in characteristic L. Okay, so let's see. Okay, so what do I want to say? Yeah, so I think that was really sort of the main things that I wanted to say for this just sort of outline. There's, of course, even after you know that this is sort of saying that there's something non-trivial about algebraic cycles on an abelian variety in characteristic 0, because, of course, abelian varieties do satisfy this conclusion of taking n to be 3. So this implies, of course, that for the universal abelian threefold X, let's say over C, the H3 with Z mod L coefficients is not all supported on a divisor. Because let's see, because this assumption about sort of ordinary reduction is no problem, because basically a generic abelian threefold in characteristic 0 reduces to sort of any abelian variety in characteristic L that you want. It could be ordinary in particular. So this is sort of saying that there's a potential for some algebraic cycles on X to be non-trivial. Then you have to argue that this particular cycle, the Terasa cycle, is non-trivial. And again, because I'm sort of willing to work modulo just some power of L, it all sort of reduces to calculations tensor Q or tensor QL or something, because I don't care about that exactly what power of L is going in there. So showing the non-triviality of the Terasa cycle mod some power. So once you know some sort of a very little bit at the beginning, like this. Yeah. Yeah, that's right. I mean, so basically, right. Maybe I'll say a little. So like, yeah. So for this sort of really general abelian variety, you can basically figure out essentially what this n1 has to be, because it will automatically be invariant under the Galois group, which is basically the fundamental group of this moduli space of abelian varieties. So this group sort of falls into a primitive part and a non-primitive part, and this basically implies that the n1 has to be just the non-primitive part. So somehow, if you only care about primitive cohomology, this is actually proving that n1 is 0 in this case. So yeah. So there's sort of a big difference between the cohomology and the, this first step in the Conneville filtration. Anyway, I just wanted to say, showing them. So once you have some basic information like that, if I just want to show that some cycle is non-trivial mod some power of L, it reduces to a computation tensor Q, tensor Q, or maybe I should say tensor QL. But in fact, yeah. So what I need is exactly sort of Haynes' proof of the non-triviality of the Terasa cycle. So it really just sort of reduces to a geometric statement, a statement sort of over C. So for some steps of the argument, you're contemplating reducing to characteristic L, but for this step, you just have to, you argue that the Terasa cycle gives you a non-zero class in H0 of the mapping class group of genus 3 with coefficients in, the primitive part of H3 of this Jacobian of the universal curve, so to speak. So how could I say this? So the Terasa cycle gives you a cycle on every Jacobian of a curve, so it kind of gives you a family of cycles over the moduli space of curves of genus 3. Yeah, those cycles are all homologically 0. So, I mean, from Griffith's point of view, it gives you a section of a certain family of intermediate Jacobians over this moduli space, and yeah, the group of such sections is basically this group. And Haynes showed essentially was sort of topological argument that the Terasa cycle is non-zero there, and sort of that's exactly what I can sort of plug into this number theory argument. Yeah, okay, because in number theory, cycles have invariance in groups like this, in sort of H1 of Galois groups with coefficients in geometric étale cohomology. So yeah, sort of putting together these various ingredients, yeah, you get this conclusion. Okay, so I'll stop there.